Okay, let's dive in. Imagine a massive, clean energy source that's not sunlight or wind, but hydrogen, just forming naturally underground.
Yeah, it sounds almost like science fiction, doesn't it?
It really does. But it's real. We're talking about naturally occurring hydrogen, sometimes called white or gold hydrogen.
And it's funny, for decades, if drillers hit hydrogen, it was like, oops, contamination or, a failed well.
Right. Just ignored it or didn't even test for it properly.
Exactly. And now that same hydrogen is suddenly this potentially huge resource.
So that's what this deep dive is all about today. Our mission is to, cut through the hype and the jargon and get you quickly informed on geologic hydrogen.
We've got a bunch of material here, a key scientific paper, expert discussions, and that brand new USGS report mapping U.S. potential.
Yeah, we're going to unpack what it is, how it gets there, where it's popping up, why it could be such a game changer, and also the big questions that are still out there.
Sounds good. So first things first, what is geologic hydrogen?
Basically H2 gas, right?
Yeah.
Just found underground naturally.
Precisely. It's not something we have to manufacture using other energy sources like we do now. It's already there in its gaseous form.
And that's so different from, say, blue or gray hydrogen people talk about.
Big difference. Gray hydrogen comes from natural gas, and you vent the CO2. Blue hydrogen is the same process, but you try to capture that CO2.
But this geologic stuff, it's not made from anything like that.
No, it's a primary energy resource itself, like finding oil. But instead of hydrocarbons, it's H2. And the beauty is, when you use it, burn it, fuel cell, whatever, you mainly just get water.
Water as the main byproduct. That's obviously huge for emissions.
Fundamentally different environmental footprint, yeah.
Okay, so how does the Earth actually make it? It's not like it's just leftover gas from billions of years ago.
Generally, no. It seems to be actively generated through ongoing processes. The main one everyone points to is serpentinization.
Serpentinization. Okay, what's that involve?
Basically, you get water reacting with specific types of iron-rich rocks. Think rocks like olivine, pyroxene, often found in what geologists call ultramafic or mafic rocks, like ophiolites.
Ophiolites.
Yeah.
Those are bits of ancient ocean crust pushed onto land, right?
Exactly. So deep down, maybe 5 kilometers or so, where it's hot, water meets these rocks, reacts with the iron, and hydrogen gas is produced.
Rock plus water equals hydrogen.
Yeah.
Got it. Any other ways?
Yeah. Another important one is radiolysis.
Radiolysis. Sounds like radiation.
It is. You have rocks like granite that naturally contain radioactive elements, uranium, thorium, potassium. As these decay, they release radiation alpha, beta, gamma rays.
And that radiation does what?
It can actually zap water molecules trapped in the rock pores and split them into hydrogen and oxygen.
Huh. Interesting. And is there a clue if that's happening?
Sometimes, yeah. If you find helium along with the hydrogen, that can be a hint, because helium is often produced by the same radioactive decay chains.
Okay, serpentinization, radiolysis. I think I saw something about even deeper sources, maybe.
Right. There's a hypothesis, still a bit less understood, that hydrogen might also be slowly seeping up from way down deep, maybe the mantle or even the core.
How would we know that?
Well, some really deep drill holes have found increasing hydrogen concentrations the deeper they go. But, the exact contribution from that deep source, still a big research question.
What really struck me from the sources was the speed this happens. It's not like oil taking millions of years.
Spot on. That's a crucial difference. Serpentinization, for example, can happen much faster. We're talking potentially days, weeks, and it can be a continuous, ongoing process.
Continuous. That's, wow. So does that mean a hydrogen field could actually refill itself?
That's the million-dollar question, or maybe trillion-dollar question. If the generation is ongoing and fast enough, you could potentially have a sustainable, almost renewable resource on human timescales.
Which is totally different from fossil fuels. Game-changing, really.
Completely different paradigm.
Okay, so if it's forming, where have we actually found it? Are there, hydrogen gushers out there?
Well, maybe not gushers everywhere, but definitely known occurrences in seeps places where it leaks naturally to the surface. The most famous example is probably in Mali, a place called Burakabugo.
Mali, right. I read about that. They hit it by accident.
Yeah. Drilled a water well back in '87, hit gas, capped it. Years later, they realized it was almost pure hydrogen, like 98% pure.
98%.
Yeah.
That's incredible purity straight from the ground.
It really is. And we're seeing reports from Australia, too, some wells hitting maybe 90% hydrogen. Plus, documented seeps in Ukraine, Oman.
And Turkey. that continuously burning seep.
Yanartas, yeah. That one's linked to ophiolite rocks, fitting that serpentinization story perfectly.
The sources also mention something pretty dramatic in Albania.
Oh, yeah, the chromium mine. It's in ophiolite rock again, and they've apparently had major problems with hydrogen gas seeping into the mine and causing explosions since the early 90s.
Explosions, so significant amounts.
Apparently. One fault zone they measured was flowing something like 215,000 standard cubic feet a day. That's not trivial.
Wow. Okay, bringing it home. What about the U.S.? Any finds here?
There have been historical reports, like a deep well in Kansas hit hydrogen in very old Precambrian basement rock. But the big news recently, which the sources cover, is that USGS report.
The one with the map.
Exactly. It's the first public map showing potential prospectivity across the whole contiguous U.S. It's not saying drill here, but it maps out regions where the geology looks favorable.
Favorable meaning having the right ingredients.
Right. Having the potential source rocks, the reservoir rocks to hold the hydrogen, and crucially, the seal rocks to trap it. They layered together a ton of different geological and geophysical data to build it.
Which kind of begs the question,
Yeah.
if it's potentially widespread, why did the oil and gas industry miss it for so long? They've drilled everywhere.
That's a really key point the sources make. Several reasons. One, the tools often weren't set up to find it.
How so?
Well, standard gas detectors or lab instruments like chromatographs often used hydrogen as the carrier gas to analyze samples. So if there was natural hydrogen in the sample, it couldn't measure it, or it just looked like the baseline.
So it was invisible to the equipment sometime.
Pretty much. And second, even if they did detect it, it wasn't what they were looking for. It might mess with drilling mud, cause bubbling. It was seen as a nuisance, a problem, maybe a sign of contamination, or a failed well for oil and gas.
So they just plugged the well and moved on.
Often, yeah. The focus was hydrocarbons. Finding pure hydrogen wasn't the goal, so it got overlooked or dismissed.
Okay, so now we're looking for it, and the potential seems huge. Why does this matter so much in the bigger picture?
It matters massively for the energy transition, getting to net zero emissions. Most scenarios see a big role for low-carbon hydrogen.
Especially for those tricky sectors, right? The ones hard to just electrify.
Exactly. Think heavy industry like cement making, where you cook limestone and release CO2 chemically, or steel production. Reducing iron ore also creates CO2. Hydrogen could be a clean fuel or feedstock there.
Makes sense. What about other uses?
Well, it could be used to make synthetic fuels, e-fuels, for things like planes or long-haul trucking. It can fuel vehicles directly or generate electricity in fuel cells. Lots of potential applications.
And the market size estimates I saw were just astronomical.
They really are. Potential for trillions globally, maybe $750 billion just in the U.S. by 2050. But meeting that demand requires a huge ramp-up in low-emissions hydrogen supply.
So finding it ready-made underground could be a shortcut.
It could potentially simplify things, yeah. Instead of building massive electrolyzers or reformers, you might just drill for it. It could streamline that whole hydrogen value chain: production, storage, transport.
Especially if it's recharging, like you said earlier.
Yeah.
Adds that sustainability angle.
Precisely. It could be a way to get low-carbon hydrogen more directly, maybe more cheaply, and potentially sustainably.
Okay, let's get into the geology a bit more. How does exploring for this compare to looking for oil and gas? Similarities, differences?
Lots of similarities, which is good news. We can leverage decades of oil and gas expertise. You still need the basic petroleum system elements, a source, migration pathways, a reservoir rock to hold it, and a seal rock to trap it.
And the exploration methods? Looking for seeps, using seismic?
Yep, all analogous. Surface geochemistry, remote sensing like seismic, gravity, magnetics to understand the subsurface structure, and ultimately drilling. The know-how is largely transferable.
But hydrogen itself is different. It's tiny. Does that cause problems?
That's the big geological challenge everyone highlights. Hydrogen is the smallest molecule. It's incredibly diffusive.
Meaning it can sneak through rocks easier than oil or gas.
Potentially, yes. There's a real debate about whether the shale cap rocks that effectively trap large hydrocarbon molecules can hold on to tiny hydrogen molecules over geological time. It might just leak through slowly.
Could it react with the cap rock too?
It could. For example, if the seal rock contains sulfur minerals like gypsum, the hydrogen might react to form hydrogen sulfide, H2S. Bad news for the seal, and H2S is nasty stuff. Plus, in shallower zones, certain microbes just love to eat hydrogen.
So finding a good seal is maybe even more critical for hydrogen than for hydrocarbons.
It seems that way, though the sources mention some potentially effective seals, like igneous rocks.
Right, you mentioned Mali had those dolerite sills.
Exactly. These sheets of cooled magma that cut through the rock layers seem to act as really good barriers there, trapping the hydrogen in compartments.
And you also mentioned something weird about water acting as a barrier.
Yeah, it sounds counterintuitive, but hydrogen doesn't dissolve well in water at all. So if you have a water layer, it can actually act as a pretty effective barrier to hydrogen bubbling up. That might explain the gas lift effect seen in some wells, where water surges out with the gas.
So different rocks might trap hydrogen compared to methane, for instance.
It's possible, yeah. Differential sealing. Maybe hydrogen gets trapped deeper by one type of seal while methane accumulates shallower under another. It adds complexity to exploration.
Let's zoom back into that Mali case study, Barakabugu. That Prinzhofer paper really laid out the details.
It's a classic example now. You had that incredible 98% hydrogen purity.
And the source. They figured that out.
They suspected deeper greenstones, those old ultramafic rocks reacting with water, but pinpointing the exact source deep down is always tricky.
Okay, and where did the gas actually collect? The reservoir.
It accumulated in porous sandstones and carbonates. Specifically, carbonates with vugs, little dissolved holes and cavities, good storage space.
And the trap was those dolerite sills you mentioned.
Yep, those igneous intrusions acted like impermeable lids. Interestingly, they also noted breccias rocks made of broken fragments acting as seals too, even though you might think they'd be permeable.
What about the other gases found with the hydrogen? What did they tell us?
That was really revealing. They found traces of methane, other hydrocarbons, helium, nitrogen, CO2. But the key was how those hydrocarbons likely formed.
Not from cooked organic matter like normal oil and gas.
The evidence strongly pointed towards an abiotic origin, meaning chemical reactions in the rock, not biology. Things like CO2 reduction or the Fischer-Tropsch process, converting carbon monoxide and hydrogen into hydrocarbons.
Which fits with the local geology being poor in organics.
Exactly. And finding relatively high levels of carbon monoxide, or CO, over 1,000 parts per million, was another big clue. CO is super reactive, it shouldn't hang around. Its presence suggested active, ongoing geochemical reactions.
Pointing toward that idea of continuous generation.
Yes, it strongly supported a non-fossil, continuously replenished source. The noble gas isotopes, like helium and argon, also pointed to a deep crustal source, not the mantle.
And that water gushing out.
Yeah.
The gas lift.
Yeah, that fits with the idea of water acting as a seal due to hydrogen's low solubility. They estimated the gas and water were roughly in equilibrium down there.
Mali really shows the concept works. Okay, pivoting back to the U.S. and that USGS map, how did they actually make it? You said it wasn't drill here spots.
Right, it's a regional play fairway map. They took all that data, gravity, magnetics, known faults, rock types, radioactive mineral locations, and evaluated the chance of sufficiency, or COS, for each component needed. Source, reservoir, seal.
Chance of sufficiency. Break that down. What does a high COS mean?
Think of it like a confidence score, from 0 to 1. It's not a statistical probability of finding X amount of hydrogen, it's more like an expert judgment. Based on the data, how likely is it that this area has a working source, reservoir, and seal capable of creating an accumulation?
So it combines the chances for all three things.
Essentially, yes. And there's lots of uncertainty built in, which is why the map scores range from about 0.15 to 0.85. I'm not saying anywhere is a guaranteed hit or a guaranteed miss yet.
And they map the sources separately, like where serpentinization might happen.
Yep. They looked for ultramafic rocks using gravity data, areas near old rift zones, surface outcrops, and that big magnetic feature off the East Coast. For radiolysis, they looked at where uranium-rich rocks like granites are common. For deep sources, they looked at major fault systems, areas with high heat flow.
And then overlaid potential reservoirs and seals.
Mostly based on sedimentary basins because sandstones, carbonates, shales, and salt layers tend to have more predictable reservoir and seal properties than, say, fractured basement rocks, although they considered crystalline rocks too.
And you mentioned the seal is often seen as the riskiest part.
Generally, yes, because of hydrogen's pesky ability to diffuse, so finding areas with proven effective seals is key.
So putting it all together, where do the maps say looks most promising in the U.S.?
The highest COS areas, say above 0.5, popped up in places like Michigan, parts of Kansas, North Texas, southern Oklahoma, western North Dakota, Montana, and the Williston Basin, the Four Corners area.
Anywhere else jump out?
Yeah, interestingly, western Kentucky and southern Illinois showed high potential. That's linked to the New Madrid seismic zone, an old rift system called the Reelfoot Rift, and areas known for mineral deposits associated with those deep-seated structures.
And that idea about hydrogen migrating sideways long distances, did the map support that?
It did seem to, especially along the East Coast. The thinking is hydrogen generated offshore, maybe along that East Coast magnetic anomaly from serpentinization, could potentially migrate quite far inland.
And get trapped closer to shore.
Potentially. The map shows higher prospectivity in some coastal plain areas, like in the Carolinas or Maryland, possibly reflecting trapping along these long migration pathways. It might even explain weird surface features like the Carolina bays, which sometimes show hydrogen seeps.
Okay, this is all super exciting, huge potential. But let's be realistic. What are the biggest hurdles, the main challenges we need to overcome?
There are definitely significant challenges outlined in the sources. First is just getting a better handle on the global resource size. We see signs, but how much is actually trapped economically? Big question mark.
And finding those traps, given how leaky hydrogen can be.
That's a major one. We need smarter exploitation techniques, better ways to detect active generation, map migration pathways, and image potential traps. AI might help eventually, but it needs more data to learn from first.
Drilling itself must have challenges too.
Yeah, the rocks involved might be altered and tricky to drill. And obviously, drilling into high concentrations of hydrogen carries significant explosion risks that need careful management.
And even if you find it and produce it, getting it to market.
Transportation is a biggie. Hydrogen can make steel pipelines brittle over time, hydrogen embrittlement. So you might need new pipelines, maybe the plastic ones mentioned, or convert the hydrogen to something easier to transport like ammonia. But that costs energy.
And leakage is a concern, right? Not just losing the product.
Right. Hydrogen itself isn't a greenhouse gas like CO2 or methane. But if it leaks into the atmosphere, it reacts with hydroxyl radicals OH molecules.
And why is that bad?
Those OH radicals are like the atmosphere's cleanup crew. They break down methane, which is a potent greenhouse gas. If leaked hydrogen uses up the OH, methane hangs around longer, increasing its warming impact. So minimizing leaks is really important.
Okay, so challenges in finding it, drilling it, moving it, containing it. But presumably there's work going on to tackle these.
Absolutely. Lots of opportunities in active research. One really cool area is trying to stimulate hydrogen generation in place.
Like speeding up the natural process.
Kind of. Injecting hot water or steam, maybe catalysts into the right kind of rocks, ultramafics, to kickstart or enhance serpentinization. There are government programs like ARPAE funding projects looking into exactly that.
And we can adapt oil and gas tech.
Definitely. Leveraging that existing expertise in geology, geophysics, drilling is a huge advantage. It needs adaptation, but the foundation is there.
Plus, work on the hydrogen handling side. Better pipes, leak detection.
For sure. Developing better sensors, new materials, more efficient hydrogen carriers. That's all happening anyway because of the broader push for hydrogen energy. And it will benefit geologic hydrogen too.
It really sounds like we're just scratching the surface, scientifically speaking.
We really are. There's a lot of fundamental understanding still needed, both in the science and the engineering. But the pace of research and exploration is picking up incredibly fast. It's a very dynamic field right now.
So, reflecting on all this,
Yeah.
what's the main thing that sticks with you about geologic hydrogen?
For me, it's just the profound idea that basic geology, processes happening deep inside the Earth right now, could offer this potentially massive source of clean energy. It really shifts your perspective on where energy comes from.
Yeah, it makes you think, doesn't it? What else is down there? What other secrets or resources are waiting, maybe hidden in plain sight, if we just learn how to look for them in a new way?
It definitely underscores that there's still so much discovery to be made about our own planet.
Keeps things interesting, that's for sure. Well, thanks for unpacking all that with us today.
My pleasure. Fascinating topic.